For this next video, we're going to discuss complex numbers. Now, to understand what complex numbers are, what they mean, I want to look at this Venn diagram showing us different number sets. Now, the most basic number set that we will talk about are called natural numbers. Now, these are just the numbers 1, 2, 3, 4, 5, 6, 18, 23, and so on. These are all whole numbers. No negatives, so we don't even really discuss positives and negatives. It's just positive numbers. You don't have to make the distinction. There's no zero, there are no decimals, no fractions, just actual whole numbers starting at 1. Now, the difference between natural numbers and whole numbers is that whole numbers include a 0. Now, that is a pretty distinctive difference. There is a big difference between a set that doesn't have a 0 and one that does. Even though it's just one number difference, there's a whole lot more that you can do with whole numbers than with natural numbers. Because like with natural numbers, you can't subtract a number from itself. 3 minus 3 would be 0, but there's no 0 here. Okay, so you can only subtract numbers smaller than yourself. But with whole numbers, you can. Right? You can always do like 3 minus 3 will come back to a 0. So natural numbers are one set, whole numbers are another. Notice that all of these natural numbers are in this set of whole numbers. Every natural number is a whole number, but there's at least one whole number, 0, that isn't a natural number. Now beyond these two sets, there are integers. Notice the only difference between whole numbers and integers is that we add on all these negatives. So this one goes forever to infinity in the positive direction. Same with whole numbers. There's a definite starting point, but then it goes on forever. Integers go on forever in both directions. So there's a 0 right in the middle, then 1, 2, 3, 4, 5, 6, 7, 83, 212, and so on. Again, all the positive whole numbers, but then there's also the negative whole numbers. So negative 1, negative 2, negative 3, negative 4, negative 18, negative 72, and so on. So all we did was add on negative versions of everything. Okay, so natural numbers, and then whole numbers, then integers. Now if you add in decimals and fractions, or basically just make a ratio of any of these integers, that's where rational ratio comes from. We can take any of these integers divided by another integer, and it would make a rational number. 1 divided by 2 is 1/2. 3 divided by 5 is 3/5. 3 divided by 2 is 3/2, or 1.5. Okay, 2.25 is the same as saying like 2 1/4, or you can think of it as 9/4, 9 divided by 4. And of course, there's a million other that you can do, but these rational numbers, it's just a ratio of integers. It includes decimals, fractions, and so on. Okay, so natural numbers, whole numbers, integers, rational numbers. Next, you go into irrational numbers. So this Venn diagram uses a different form to look at irrational numbers. I want you to more so think about it's any time that you can't make a ratio, but you still know what that number is, like the square root of 2. Square root of 2, if you type it into your calculator, will give you a very long decimal number, but that decimal number is not exact, right? It keeps on going for a long time, so it is irrational. Same thing with pi. Pi goes on forever, so it is called irrational. Okay, so we can find all of our irrational numbers, or we can write them as just simple things like root 2, or negative root 3, or pi, or e. We will talk about e later, but these are all irrational numbers. Now, if you have all your irrational numbers, which are technically supposed to be outside of rational numbers, they are separate. There's rational and irrational. They all make what are known as the real numbers. Okay, we can actually find those and use the real number sets. Now, beyond real numbers, there are imaginary numbers. Okay, and imaginary numbers are what we're going to be discussing today. Now, if you put the set of real numbers and the set of imaginary numbers together, we call that complex numbers. So notice, a complex number is one like 4 plus 2i. This 4 is what we call the real part. This 2i is what we call the imaginary part. So complex numbers have both a real and an imaginary part. But that's basically what complex numbers mean or where they come from. So let's kind of discuss a little more about what complex numbers do or how we got them. So when we talk about solving using a quadratic formula, here was our regular quadratic function set equal to 0, and we have our quadratic formula here. Now remember, we talked about the discriminant being b squared minus 4ac. When the discriminant is positive, we know that there are, and I suppose I could draw it out, then I'm going to go like this. Here's my parabola. When the discriminant is positive, there are 2 spots where it hits, so there are 2 zeros. When the discriminant is 0, we have the square root of 0, which there's only one answer to, so it just touches 1 time. Now if the discriminant is negative, this will never ever touch this line. So we'd say there's no real zeros, or there are 0 of them. But technically there are still 2 complex or 2 imaginary solutions. Okay? And that's where this idea of a complex number came from. You're using the square root of a negative number. So what imaginary numbers are, it's basically I. I is what's known as the imaginary unit, and I basically means the square root of -1. So if we've got things like square root of 16, you just simply call it 4. Square root of 49, you simply call it 7. Square root of -1, you simply call it I. And that's where imaginary numbers come from. So if you wanted to simplify radicals, so if we had like a square root of 48, you could break that apart into square root of 16 times the square root of 3, right? Because 16 times 3 is 48. They're both underneath the square root. So we break it apart into 2 pieces. And I specifically chose 16 because I know square root of 16 is 4. So we would call this 4 square roots of 3. This piece is 4, still times the square root of 3, so 4 square roots of 3. This is how we can simplify this square root. I'm going to show you another one. Square root of 150. I break it apart into square root of 25 times square root of 6. 25 times 6 is 150, still under the square root. Break them apart. This one simplifies to 5. Square root of 6 would simplify into 2 and 3, but we don't know the square root of either of those. So this is as simple as that 6 is going to get, so we just call it 5 square roots of 6. Now, if we are simplifying radicals that have a negative, this is what you need to do. You're going to break them apart just like we did up here, but you're going to use this imaginary unit, I, as the square root of -1. Anytime you see square root of a negative, break off this square root of -1 as one of your pieces. So now, square root of -16, we call it square root of 16 times square root of -1. This is 4. This is I. So we call it 4i. Same thing if we have square root of -50, we break it apart into 3 different pieces. Square root of 25, square root of 2, and square root of -1. This negative breaks apart as its own, then 50 breaks into these 2. This is a 5, this has to stay, and this becomes I. So 5 times the square root of 2 times I. Notice that I is not underneath the square root. It is separate. We put it at the end the same way we would write like 4x. We don't call it x4. We put the x at the end. We're going to put I at the end as well, but we need to make sure it doesn't go underneath any of these radical symbols, under the square root. So this would be your simplified form. Now technically, as we discussed before, square root of 16 would actually be positive or -4. So all of these would actually have a positive or negative out in front of them. positive or negative 4 square roots of 3, positive or negative 5 square roots of 6, positive or negative 4i, and even positive or negative 5 square roots of 2i. Okay, I suppose I could write this one in. There we go. So this is how you would simplify any of our complex radicals. Now let's talk about the powers of I. A lot of times you'll see I just alone. Remember, that's simply the square root of negative 1. So if it has no power, remember that's kind of a hidden 1 up here. So I to the first power is still just square root of negative 1, which we simply call I. So this is an important power of 1. It is the first power. Now if we look at I squared, you're basically taking this square root and squaring it. And as we've looked at before, when you square a square root, those cancel out, and whatever was left over, that's your answer. So I squared, we simply call negative 1. It's the only time where you can square a number and it'll equal a negative, right? It has to be an imaginary. Now, I cubed, I to the third power, I want you to start thinking of it this way. I cubed is the same as I squared times I, or I'm going to write that I to the 1. Right? We've discussed before how like a variable to a power times a variable to the power, we add these together. So to get I cubed would be power of 2 plus power of 1. Now these two we've already simplified. I squared was this negative 1. I to the 1 was this I. Right? Now we can spell it all out the same way we spelled these ones out, or you can just jump right ahead to say I squared is negative 1, I to the first power is I, negative 1 times I, we would just call that negative I. So these form our first three powers of I. I to the 1 is I squared is negative 1, I cubed is negative I. Now, the last, and probably still one of the most important ones, is I to the fourth power. Just like with 3, we can break it into I squared times I squared, which, again, you could break into these two separately. Right here, goes here and here, and we would say, okay, this cancels here, this cancels here, so we would have negative 1 times negative 1. But again, remember, if we already figured out that I squared is just negative 1, we could also just go from here and say negative 1, negative 1. Negative 1 times negative 1 is positive 1. So I to the fourth power is just simply 1. Okay, these four are your most important powers of I. As long as you can remember these, everything else falls into place, and I'll show you why. We're going to do a few more of these, but remember, these are really the only four you need to know. I to the fifth power, you can break apart into I to the fourth times I to the 1. Now we've already said I to the fourth is 1, and I to the 1 is just I, meaning we've got 1 times I, which is just I. Simple enough. How about I to the sixth? I can break it apart into I to the fourth times I to the 2. I already know I to the 2 is negative 1, so 1 times negative 1 must still be negative 1. I to the seventh is similarly I to the fourth times I to the 3. This I to the fourth is just 1, and this I to the 3 is a negative I, so we would just call it negative I. I to the eighth is just two different I to the 4s. Each of those are 1. 1 times 1 is 1. Notice this pattern, I, negative 1, negative I, positive 1, is the same as these ones. I, negative 1, negative I, 1. We're just going to keep repeating this cycle as we go. But instead of thinking of it as repeating this cycle, notice all we're doing is taking out differing amounts of I to the fourth power. 9 is 4, 4, 1, right? 4 plus 4 plus 1 makes 9. I to the fourth is a 1. This I to the fourth is a 1. I to the 1 is just I, so this must be I. It's like the beginning of this cycle, or the beginning of our very first I to the first power. Same thing, I to the 10 is I to the 4, I to the 4, I to the 2. Those I to the 4's are both 1. This I squared is negative 1, so it must be negative 1. Notice, I, then negative 1, I, then negative 1, I, then negative 1. So the trick for these, or the pattern, is that you're always subtracting the biggest multiple of 4 away from the power of I. Then you just simplify using the powers 1 through 4 of I. So as long as you know I to the 1 is I squared is negative 1, I cubed is negative I, and I to the fourth is 1, you can figure out any of the other powers of I. So let's try a few of these on our own here. If we've got I to the 23rd power, we're going to subtract the biggest multiple of 4 that we can. Now we could subtract 4, we could subtract 8, we could subtract 12, we could subtract 16, or even 20. So let's subtract the largest one, 20, and say that 23 minus 20 is just 3. So I to the 23 is the same as I to the 3, which we know for sure is negative I. So I to the 23 simply comes down to just I, or negative I. Let's try I to the 67. Again, think about all the 4's that you can take out. Obviously, we can take out 40, so I'm going to call this 37. Now, if you could go even higher, go ahead and simplify it even more. I just took out 40 because that one is pretty obvious. Now, from 37, let's think of other 4's that I can take out. Well, over here, we knew that we could take out 20. So let's take out 20 from here. This would come out to 17 then. Now, looking at 17, another 4 that I could take out would be 16. I'm going to take 16 away from that and leave just I to the 1 power. I to the first power is just I. So I to the 67th will just reduce down to I. We're going to do this I to the 16th 2 ways. First, I'm going to think of it as I'm going to subtract 12. If I subtract 12, I get I to the 4th. I to the 4th then, remember, is 1. So you can do it simply just by taking away the next closest 4, and it would come out to I to the 4th is obviously 1. However, this 4, or even this 16, could be simplified even more. 16 is a multiple of 4. So what if I took away 16, leaving I to the 0? Remember, anything to the 0th power is always 1. So even if we took away exactly on this 16, we would still come out to this 1. It would be the same thing. So that'll help us with our powers of I. Let's try another larger one here. Okay, I to the 731st power. Well, again, I can always take out multiples of 4. So the first thing I'm going to take out is 400. Take away 400 from this and you get to I to the 331st. Okay, again, looking for powers of 4. I know that 4 goes into 100 because 4 quarters make $1. So I can always take out 100. So 300 minus 100 gets me here. Well, I can take out another 100, and then I can take out another 100. In fact, a nice trick is you can always take away any 100s and beyond. So we really only need to be concerned with our 10s and 1s digits. From here, notice this 31, the same as this 31 because we took away 700. Now I need to start taking away 4s. So I can take away 20, just like we did up here, and call it I to the 11th. I can take away 8, because I know that's another 4, would be 8. So I to the 3rd power is negative I, just like we had up here. So we can simplify I to the 731st to just being negative I. Now again, if we can take away any 100s that we want, then we can take away from here over. Right? Just take away any of those 100s and beyond. So this first simplification would be I to the 45th power. Well, obviously, we can take away 44. That's 4 times 11. So that's good to go. That's now I to the first power, which of course, again, is just I. So that would be our simplification of any powers of I. Now, if we're trying to simplify complex expressions, that's a little bit different. This is going to be similar to simplifying radical expressions that don't have complex numbers. And we'll actually get over that in our next video.